Okay, hello and welcome. This is SFU Math 232. I hope a relatively short lecture, just a midterm review. There's absolutely nothing new in this lecture at all. I'm just going to go over some of the main topics that we've covered, say what they are, and just do a couple of problems. If you feel confident with the material, there's really no reason to listen to this lecture. If you want to just sort of go through it, thinking to yourself, oh, do I know what that is? Yep, check. Do I know what that is? Check. That might be a good thing. So yeah, here we go. What have we done so far? So let us just talk about a couple of things, organizational things. Today we had an in-class Zoom. It was this morning. So what is that? This morning. That was, let's see, I'm looking at the date here. That was October 2nd. Okay, we talked a little bit about the logistics of the midterm. I've sent out several announcements through Canvas, so please read all of those. There is, that's in Canvas, there is midterm review information on the exam resources page, so check that out, resources page in Canvas. The midterm is covering Chapter 1, Chapter 2, and Section 3.1. That's the coverage. These are just the very basic bare bones details. It's 45 minutes long. We have 10 minutes to upload. Okay, there is important information in these Canvas announcements about the what I have question 0, which is the academic honesty statement that you should prepare in advance. I want you to, and I expect that you'll read those announcements and follow them. Okay. All right, so let's just briefly go through what sort of things we have been doing since the beginning of the semester. So we started the semester with Chapter 2 of the BUS-B textbook. That's what we're following, Chapter 2. What are the sort of main things here? I'm just going to sort of list out what I see the main things. In our exam resources, there's actually a much more detailed topic review, so covering everything that we've talked about to alert you to all the things. But this is what I'm sort of seeing the main things to be. What is a system of linear equations? So that is we learned what is a system of linear equations. That's clearly important. So that means we have several. Let me just give some example. We have one or more linear equations. Let's go 2x1 plus x3 x2 minus x3 equals 10. Okay, so we have some number of, I can already see that this is inconsistent. I don't know why that bothers me, but okay, so we have a system of linear equations. It means we have more than one of them. We can have some number of variables. In this case, I've got 3 variables, and we can have some number of equations. So we learned, we know what that is, and then we learned how to represent this in an augmented matrix. Okay, so I'll just do this example here. I'll represent this linear system in an augmented matrix. That would be 3, 3, minus 1, 10, 1, minus 1, 1, 6, 2, 3, minus 1, 15. So we learned how to represent it in an augmented matrix. We also learned that you can represent it like this, AX equals B, where in this case A, X, and B are vectors, and this is called the coefficient matrix. Okay, so for the example that I just concocted now, that would look like this. A would be this guy here. And then I would write it multiplied by X, and that would be equal to B. Okay, so this right here is the coefficient matrix. This longer guy here is the augmented matrix. Okay, then we learned how to solve the linear system. So we had then solving the linear system. And how did we do that? Well, we had Gaussian elimination. We had Gaussian elimination. And then we took, and that took us to what we called row echelon form. And then we also saw Gauss Jordan elimination, and that took us to the reduced row echelon form. Row echelon form. Okay, so if we just did the Gaussian elimination, we saw that we could solve the system as well following the Gaussian elimination by using back substitution. Okay, so you should be able to recognize when a matrix is in row echelon form and when it's in reduced row echelon form, and then understand how to write out the solution for the system given what you see in the matrix. Okay, we a bunch of words. I'm just going to jot them down here. You make sure that you know this. You need to recognize if this term is used. It's a homogeneous system. What does that mean? It means that B is equal to 0. Okay, if the system is consistent, that means it has at least one answer, at least one solution. The opposite of that is inconsistent. We mentioned the coefficient matrix. You need to be able to recognize in the augmented matrix what are the leading variables and which are the free variables. You need to understand what are the possible outcomes when you solve a linear system. When I take a system of linear equations, I attempt to solve it. What are the possible outcomes? So what possible outcomes are there? And that is, there is no solution. That is a possibility. There is one solution. That is another possibility. And there are infinitely many. Solutions. Okay, so that is something that you should definitely be aware of. We've seen the role of parameters. So sometimes we've seen these kind of questions where, for what values of C is this matrix invertible? For what values of C does this system have a single solution, etc. So you have to understand the role of parameters. We've seen the special matrix I, the identity matrix, and we saw some applications of solving problems in with circuits, balancing chemical equations, looking at network flow, what that you can use, you can set up an augmented matrix for, and you can solve and find out what the solution to the practical problem is. Okay, that was basically the thrust of chapter 1. So that's sorry, chapter 2. We did chapter 2 first, which is why I'm doing them in this order. Did I put that up here? Yes, I did. Chapter 2. So we did chapter 2 first, and those are sort of the basic ideas of chapter 2. Sort of building on what you already knew coming into the course. You've already seen 2 equations, 2 unknowns, 3 equations, 3 unknowns, and then knowing already what it means to solve this and that sort of thing. So we started there, and then we went back to chapter 1. And we looked at things, we defined a little bit more vocabulary, and then we looked at things a little bit more abstractly. So let's just say what some of the important things were from chapter 1. We learned what is a vector. Okay, and so we would write our vector like this. It is an n tuple. So here's an example, a 3 tuple. There's 3 items in there. So this is a vector V. This vector is in R3. Okay. It's got 3 components to it. There was a little bit of a difficulty understanding what's the difference between a point and a vector. And if we were to consider this to be a point, then this vector is the vector that has ends. Its terminal point is this thing here. Okay, we're also sometimes represented depending, so this is an algebraic representation, sort of divorced from any geometric representation. And then we have also saw that we could take our vector and we could think of it as a column vector, which would mean it would look like this, 1, 2, 3, and we'd be thinking of it as a 3 by 1 matrix. That is a column vector. We also could have a row vector, and then it would look like this, 1, 2, 3. And that is a 1 by 3 matrix. So we can have this sort of column vector, row vector. We can have an algebraic representation, and then we can also represent them on a graph. So we could draw it like that, V like that. This is a different. Let me call this V1. You know, this is I don't know, 1 and 1 in fact. So we can represent them graphically like this. Okay. And we always are starting the vector at the origin. Okay, what should we know how to do with these guys once we understand what they are? We want to be able to add, subtract, multiply by a scalar. So those operations we should be able to do. The adding and subtracting, you want to be able to do that both algebraically by adding the components, or subtracting as the case may be. Algebraically, you also want to be able to do that geometrically by drawing the vectors like that, V and say W, and then recognizing that you can put the W here and that this thing right here is V plus W. Okay, so you can either add the components, that way you can easily do it algebraically, or you can also do it geometrically. Okay, we also learned how to multiply vectors. Okay, and to multiply vectors, we have learned the dot product. I have seen a couple of you using this. We have not yet touched upon the cross product in this course. So I am discouraging the use of it. It is true that you can sometimes use that for some of the problems we've been seeing, but I much prefer you just solidly learn what the course material has been so far, and that you would solve the problems that we have with the methods that we've used. The problems are designed to be solved by those methods, so we do not need to use the cross product. If you don't know what that is, don't worry, we haven't covered it. But there's two ways of multiplying vectors. We've only learned one of them. We learned the dot product. Okay, so where are we at? We learned the dot product. It's one type of vector multiplication. So if we were to have two vectors, u1 equal to 1, 2, 3, like that, and u2 equal to 4, 5, 6, like that, then we would have u1 dot u2, and that would be 1 times 4 plus 2 times 5 plus 3 times 6. Okay, a scalar number comes out to a scalar. That's important. The dot product comes out to a scalar. We saw the norm of a vector. That is the distance from the origin. So the norm of some vector v looks like this: the square root of the first component squared plus the second component squared, all the way to how many ever components you have squared, and then you take the square root. It is the distance from the origin to the terminal point on the vector. Okay, we can take a vector v and we can find a unit vector. Okay, so a unit vector. So if I was going to consider u to be the unit vector of v, I would divide the vector v by the norm of the vector. Okay, this norm is also just a number, right? This is a number. Okay, if I divide the vector by that number, the length of the resulting vector is 1. Okay, we touched upon what are the standard unit vectors. These are the vectors that lie along the axes. This is true in all dimensions, but let's just take the three-dimensional example here. These are the standard unit vectors. The one that's here, this is position 1. This is going along here. That's also 1. That's along there. That is 1. Those are the standard unit vectors. It is the case that the norm of a vector is the square root of the dot product. Okay, they are related in this way. What else? Oh, importantly, we realize that the dot product is telling us something about the orientation of one vector to the other. So the dot product is telling us this. Well, it's telling us a couple of things. If the vector u is perpendicular to the vector v, then the dot product will be 0. Okay, so if I take a dot product of two vectors and it comes out to 0, I can conclude that the vectors are perpendicular to one another. If it doesn't come out to 0, I can find out what the angle between the two vectors are. And that is the angle between two vectors, u and v, is the dot product divided by the norm of u times the norm of v. Okay, so that was some portion of the stuff in chapter 1. There's also other words that came up. So we had here this perpendicular condition. This we have also termed orthogonal. So if two things are perpendicular to one another, two vectors are perpendicular to one another, we call them orthogonal. If there's a whole set of vectors and they're mutually in pairs orthogonal, we call the whole thing an orthogonal set. We also had the word orthonormal. And orthonormal means orthogonal plus the vectors are unit length. We saw the Cauchy-Schwarz inequality. This was, I think, one of the hardest proofs we had. What does the Cauchy-Schwarz inequality tell us? The absolute value of the dot product, that's some number, is less than or equal to the norm of the vector multiplied by the norm of the other vector. That's the Cauchy-Schwarz inequality. What else do? We did the vector and parametric equations of lines and planes. Okay, so the base thing here is a line looks like this. This is a line. It is the set of all vectors. This would be what I'm going to write down here is a line going through x naught parallel to the vector v. Okay, so that is the vector equation of a line. And then we had a plane. The plane looks like this. The set of all vectors containing the vector, containing the point x naught plus parallel to the plane formed by the vectors v1 and v2. Okay, so we can write these things in vector form or in parametric form. Chapter 1 actually had a lot of stuff in it. It has a lot of new words, new concepts. I don't know if that is anything is really particularly hugely difficult, but you have to sort of soak in all these new words and then be able to use them correctly. So there's actually quite a bit in chapter 1. I think in some ways more difficult than chapter 2. Okay, and then at the end of this, we only started chapter 3. And we did section 3.1. In this chapter, we started out, and what we're doing is we're looking at sort of matrices on their own, right? We had first seen them as basically these things where we can abstract out the information from systems of linear equations. But then afterwards, we saw that we could generate a matrix by looking at network flow or providing an incident matrix on a graph. So these things could be generated in other ways. And so then the chapter 3 sort of starts out, let's just look at the properties of matrices sort of divorced from any particular way of how we got this. So we just take a look at the matrix. It is some rectangular array of entries like this. That is a matrix. It's got some number of rows and some number of columns. We saw how to add subtract these guys. We also saw how to multiply by a scalar. Okay. We saw how to multiply two matrices together. This is the important part of section 3.1, multiply two matrices. And then is the incredibly important fact that this statement holds. It is not true that when you have two matrices, that if you multiply them in one order, then you multiply them in the other order, that you would expect to get the same thing. Okay, AB not equal to BA. So that is a key feature of multiplication in this world we're operating that is different than any systems that you may have seen before. So that is the key feature from section 3.1. We saw two other things which we will find useful in the future, and we saw the trace. That was the sum of the diagonal entries, and we saw the transpose. That is when you switch the rows and columns. Okay, so that pretty much just hits on the major items for chapters 1, 2, and 3.1. There's a much more detailed list of all the topics in the exam resources page where it has what it's called, midterm 1 review, something like that. It's obvious when you take a look there what it is. Okay, so now what I'm going to do just to conclude this, I don't want to go on too long. I'm just going to do 3 problems. I took these from the textbook pretty randomly, but I thought so they might just illustrate something or remind you of things. So let me just, for example, I took from page 38 of the textbook, question D1. So here we have a we want to find the line, asking for it parametrically in R3. Maybe I should say find a line, parametric representation in R3 through this point, x naught, y naught, z naught. Some point, that's a point, through a point, perpendicular to this this line, which is given parametrically. Okay, so we want to find a line perpendicular to this line here, given parametrically through this point. So the first thing I'm noticing is that we want the line to go through this exact point. Okay, so the line that I'm going to try to find, I'm going to call it, let's just me call this what I'm looking for, x2, and it's going to go through the point. It's going to be there, and it's going to be parallel to some vector. Okay, that is the equation of a line. And then I want it to be perpendicular to this line here. So that means that the dot product of this vector here, that means this dot product, the dot product of A, B, and C with D, E, and F has got to be equal to 0. That's what's going to ensure that it's perpendicular. So then I can simply write out that dot product, and I see that that means that AD plus BE plus FC has got to be equal to 0. And I can just, I have here now one equation and 3 things I'm trying to lock down. So there's clearly more than one choice here. Here's one choice. I'll choose C equals, not C. I want to choose, I need to identify what D, E, and F are in the vector I'm trying to find. So I'm going to just choose F is equal to 0, D is equal to B, and that would force E to be equal to minus A. Okay, so that is what I'm going to end up with the vector I'm looking for. You can put that in and make sure that this expression here goes to 0. That means that my vector will look like this. X naught, Y naught. Here's a possibility. Well, maybe I'll write it out parametrically because that's how the other line was written. So I'm going to have this as x2. It's going to look like that. Let's go ahead. Let's try that. For this x2, it's going to have an x component. Now, how should I enable this? I guess I should call this x2 is going to be equal to x naught plus what is the first component, b, and then y2 is going to be y naught, and then we have e is minus a, and then z2 is z naught, and c is 0. F is 0, I should say. Here, this is F is 0. Okay, so we're done with that problem. So I mean, there's lots and lots of these problems in the textbook. Find this plane parallel to that plane, find this line parallel to the plane, find going through this point, etc. To practice enough of them so that you get familiarity with those kind of questions. Okay, another problem, page 62, D1. Just again taken somewhat randomly. Here, here's the what they're asking about. There it is. So what it's saying is, here's a system of linear equations. This system of linear equation has only the trivial solution. Okay, so then what can you say? What type of solution does this, if I put the same system of equations and I generate some numbers here? Yeah. Okay, so there I've got a non-homogeneous system with where this part is exactly the same as this part up here, and this one up here, because of this here, that b is equal to 0. That is the homogeneous one. And I know that this guy up here has only the trivial solution. That means the only solution is that x, y, and z is equal to 0, 0, 0. That's what it means. It has only the trivial solution. That is, it has one solution, and it is the 0 solution. Okay, so what does that mean? That means that if I take this matrix like this, A1, A2, A3, B1, B2, B3, C1, C2, C3, 0, 0, 0, and I row reduce it, keep going, all the steps that I would need to do, it only has the trivial solution. So I would expect what will happen is at the end of the day, this will look like this. When I get it into the reduced row echelon form. And then I would be reading the solution off of here, which would be x equals 0. Well, I would go from the bottom, so I would start down here actually, and then I would be reading off the solution z equals 0, y equals 0, x equals 0. So that's the case. Now I'm saying, what happens when I change the b on the right-hand side? So I'm going to change this guy right here. Okay, I'm going to go through doing all my row reductions. So this exact same thing is going to happen right here, right? I'm going to do exactly the same steps to get to there, but instead of having zeros here, so here I'm going to over here put 3, 7, and 11. And then over here, I'll end up with some other numbers. It doesn't matter. I don't know what they are. K1, K2, and K3. What are the possibilities? Can I have infinitely many solutions? No, I cannot. I have a leading variable in each row. So I can't have, there's no free variables. So I can't have that. Also, I cannot have a situation where I have a 0 here and some number here, because I know there has to be a 1 here. So now I'm in the situation where I've got a unique solution. So the only possibility here is a unique solution. Sorry about that. My phone is ringing. See if I can somehow mute this thing. Don't know how to do that. Okay, I still have one of this home phones that's about 25 years old. Okay, sorry about that. So what we have is, if the homogeneous system up here has only the trivial solution, then down here we can see by reasoning about what has to happen during the Gaussian elimination that we only have the possibility of a unique solution. Yeah, that's the kind of question that you sort of just going for understanding what can happen. Let me just do one other question. This is a very straightforward question. This is a D1 on page 93. We talked about this a little bit in the lecture today after the quiz. So if we have, so the question here is, here you have a product AB, and that product, whatever that matrix is size 6 by 8. What are the sizes of A and B? Okay, so we are multiplying A times B. That means that the multiplication has to be possible. So I'm saying that A, it will have some dimension, n by P. I'm not putting any restrictions on what those might be yet. And then if I'm going to multiply it by B, and I'm going to be able to do that, this number is going to have to be a P, because otherwise I won't be able to do the multiplication. The number of elements in the row, in each row of A, I have to have the same number of elements as in each column of B, so that I'm able to do the multiplication. Okay, so this is going to be P by M, some other number. I haven't specified what that must be. So then when I do the multiplication, these two things will, those two things are equal, and then the multiplication will be possible, and I will get AB, which will be of size n by M. And that tells me, because I want it to be 6 by 8, that tells me that n has to be 6 and m has to be 8. That means that A is a 6 by P matrix, and B is a P by 8 matrix, and P is some positive integer. Okay. All right, just a few questions. It's very random. Some basic just discussion about what we've done so far. There's lots of review materials in Canvas. We've done a lot of problems. The homework assignments were quite long. There was many problems to do. The best strategy, I think, for you over the weekend is to do as many problems as you can. Post things to the discussion board. If you don't know the answers, I will. I am not sure how much response we'll be able to get over the weekend, but I mean, other students can help one another in this way as well. Okay, I will see you guys Monday at before, really, we want to get going right at 11:28 when the exam comes, so you'll be there early enough so that we can get the cameras on, and we will have the midterm 11:30 on Monday. Have a nice weekend, everybody. Bye-bye.